Hello! Today we are going to talk about alternating current. What is alternating current? Alternating current or AC is an electric current that changes its magnitude and direction direction periodically. Meaning the value of current will change. Changes its magnitude, meaning the value of current will change, and its direction will also change as well. Periodically, meaning with timing, not simply change. Okay, so alternating current can be represented using a waveform. Waveform can be any waveform. This can be displayed using an oscilloscope. So it can be maybe in the form of a square wave current time. See, it can be recorded as a square wave. Or it can also be recorded as a saw wave. But its pattern is repeatedly, repeating the same pattern. So what we are going to discuss is the sinusoidal wave formed by an alternating current. So sinusoidal wave will be like this. Okay, so we know that if it is in the form of sine graph, that means it obeys the equation I equal I naught sine omega t. If you want theta, okay, then your x-axis will be theta. Okay, so the maximum value or the amplitude or what we call peak value will be here and also here, which is negative I naught for this case and I naught. Okay, meaning this is I naught. So we know the peak value occurs when sine theta is equals to 1. Okay. So alternating current source will usually be represented by using the symbol like this or just like this. So we know, oh, this is an AC source. Okay. So how to sketch a sinusoidal graph? We know sine graph, it increases from 0, meaning the value of current increases from 0, then decreases, okay, change direction, and then change direction increases and decreases, then change direction again, increases and decreases again according to time. So this is the current. So what you need to know in order to interpret a sinusoidal graph is you must know the value of maximum current or what we call peak current here or here, but at opposite direction. Okay, then you need to know if this is against time, meaning you need to know that one cycle, one complete cycle, it takes around 1 period. Period is the time taken to complete one cycle. So you can extract two information from this graph. For example, let's say this is 2 and this is 4, meaning the period will be 4 minus 2, which is 2 seconds. Because from here, point A to point B is also considered as one cycle. Simple, isn't it? Knowing this value, then you can calculate frequency. Frequency is the number of cycles that can be completed in 1 second. Means how many cycles you can complete in 1 second. For example, 2 hertz. So what do you mean by 2 hertz? 2 hertz means this current can make 2 cycles in 1 second. It means 2 cycles in 1 second. As simple as that. We can also measure in terms of angular frequency. Angular frequency. More suitable to call it angular frequency rather than angular velocity here. Okay, because we cannot see the displacement, angular displacement here. Okay, so angular frequency is 2 pi divided by time in terms of radian per second or in terms of revolution per minute or per second. Then it also equal omega or angular frequency is also equal to 2 pi f. Let's take a look at the sinusoidal equation for current. Let's say we have current equals to 4 sine 2 pi t, where current is measured in ampere and time is measured in second. So from here, if we compare to the general equation, I equals to I naught sine omega t, we find that the value of 4 here is represents peak current, and the value of 2 pi here will represent the value of angular frequency. That means from here I can extract the information or interpret the equation as I naught is 4 ampere and angular frequency here is 2 pi radian per second. So knowing this, then I can calculate root mean square current, which is I naught over cert2, that means 4 divided by cert2, and then you will have the answer. Same here, I can also calculate, maybe I would like to calculate period. So I know period equals to 2 pi over angular frequency. So I just substitute 2 pi over 2 pi, so the answer is 1 second. Or maybe I want to calculate frequency, so 1 over period. Or I can use frequency equals to frequency equals to angular frequency divided by 2 pi. This equation come from angular frequency is 2 pi f. I can also use it, maybe they give you an equation V equals to 5 cos 3t, where voltage is measured in volt and time is measured in second. So from here I know maximum voltage or peak voltage here is 5 volt and angular frequency here is 3 radian per second. SI unit for angular frequency is radian per second, right? So I also know that the phase angle, meaning if current is given in terms of sine, then I know that my voltage is 5 sine omega t or 3t here plus pi per 2. Meaning this equation and this equation is the same actually. So from here I know the phase angle is pi per 2 radian. Meaning the angle between voltage and current is pi per 2 radian. So I can calculate from here, I can use the peak voltage to calculate root mean square voltage. I also can find my period using the angular frequency here. I also can calculate frequency from this value. Since the value of current changes continuously and periodically, meaning what is the effective value of current to be used in our calculation, or what is actually the current that we receive if our power supply is in alternating source? Have you ever thought about it? So if we look here, you say, oh, this value changes from between I and I naught. So we say, yeah, let's take the average value lah. Okay, if you look at this graph, where should the average value be? Of course, it will be here, isn't it? So what's the average value here? You find that average value is 0. Meaning what? We did not receive any current when we use alternating current source. Shouldn't be, isn't it? So we cannot use this value to be our, which is to be our effective current, because it's not logic. So we are going to square our equation. Means this graph is I equals to I naught sine omega t, isn't it? So what if we square the equation? Then we will have I square equals I naught square sine square omega t, right? That means our graph will be shifted upward. That means we will get a graph like this. We will get something like this. So this will be I square, and this will be I naught square, right? And this will be 0. Meaning our values of I naught square ranges from 0 to I naught square. That means the average value should be somewhere here, isn't it? Isn't it? Okay, so if it is there, that means I average equal half of I naught square. Correct? Oh no, I square average equal half of I naught square. That should be correct, isn't it? So, meaning in order to get I, then what shall I do? I have to square root I average square in order to get the current value of current, because this is square of current means ampere square. So in order to get back current, that means I have to square both sides. So what do I get? I get 1 over cert 2, right? And I naught. Okay, so what do you call this? So this is called mean square. This is average square. We also call it mean square. So when you square root it, then it becomes root mean square current. So we simplify the symbol as I root mean square, or we call it root mean square current, equal I naught over cert 2. So same goes for the voltage as well, because alternating source will produce alternating current, meaning the voltage of the source has to be alternating in order to produce alternating current, meaning the voltage will also be root mean square voltage equals peak voltage divided by cert 2. So what is root mean square value? What does it represent? So it can be root mean square value of current. It can also be root mean square value of voltage. So it means this is the effective value or a stable value that we use from an alternating source. Because if our current is like fluctuating, meaning changes periodically like that, meaning if we look at the light source from a power from an alternating source, you find that the light will become start from dark, become bright, and then increasing brightness, then decreasing brightness, and then increase the brightness again, and then decrease again. So that is what we are supposed to see. But we don't look at it like that, isn't it? Like our filament light, we don't see the light, how to say, increase in brightness and then decrease in brightness like that, isn't it? So why? Because what we obtain here is the effective current atau brightness from the effective current or power dissipated using effective current or effective voltage. Okay, so we call this a stable value lah. So in terms of calculation, meaning how do I know this is a stable value? So we compare, meaning using an alternating source, okay, and a resistor. Then with the same resistor, we connect it to a direct current source. Direct current source, meaning the power dissipated here, as we know, equals to I square R, will be the same as the power, same value as the power dissipated here. Here we call it average power because the value of power also varies. So average power here is also equal to I root mean square multiply with R, meaning if you are using the same power and the same resistor, we can calculate the value of current. And this value of current must equal to this value of current because the power dissipated is the same and the resistor that we use is the same. So if you get this current, so we call this, the current that you calculated here will be known as root mean square current for this alternating source. Okay? Please note that this factor of 1 over SERT2 is only applicable for sinusoidal wave. Meaning in other waveform, there will be different type of value. Okay? And then, as for the equation, I equals to I naught sine omega t. This omega t is known as phase. Phase means timing. Okay? So in order to study more about this alternating current, we need something called a phasor diagram. So what is a phasor diagram? A phasor diagram is just a rotating vector that represents either current or voltage. I have here an example. Maybe we have one rotating vector, meaning it will rotate with an angular speed of omega lah, with an angular frequency. So this vector, maybe I use this vector to represent current. So it will rotate with a timing of angular frequency. Okay, so maybe I have a longer one to represent voltage. So we can see here how is it related to our sinusoidal graph. Okay, let me draw an axis. Okay, let's say I want to study about current, and then this is the time taken. So if I start from the initial point here, meaning I will measure the vertical component of this vector. Okay, so let's say at time t equals to 0, the current is at 0. So after some time, this this current, it will increase its magnitude and changes its direction. So let's say at a certain time, it is at this position. So at this position, we will take this value. So we will sketch here like this. So after some time, it's going to rotate. So it's going to move up and then move up until its maximum, meaning this maximum and this arrow should be at the same line. Okay, so like this, and then it's going to go the other side, rotate to the other side. So it's going to come down and then go like that. So it will form a sinusoidal wave like this. Let me show you. So let's say this is the vector. Okay, this is the current. Then this is the graph I'm going to sketch according to this rotating vector. So meaning here time is 0. As it goes up, maybe until here, it will take quarter period to reach here. So this will be 1/4 period, and then for it to reach this point, it will take half period. So after that, it's going to rotate until here. So it will be at this point, at this position, and then come back here and a cycle is completed. So here we can see, using a phasor diagram, we can see that this current has completed one circle here, meaning it has completed one cycle for the current. Okay, against time. So this value is the maximum value or amplitude, or we call that peak value of current on both sides, just opposite direction. So the peak value is I naught. The negative is just to show the direction, that's all. Okay, so if let's say I were to start at this position, okay, my current, so then my graph will be here. Meaning at time t equal to 0, I will be at this point. And then after some time, it will move down here. And then go down. Okay. Then go up and goes up and down. So this is also known as one cycle. So the time taken here will be one period. So if the graph is like that, of course, we can form the equation. So I will be I naught cos omega t, isn't it? So from here we will know, meaning next time when people show you a phase diagram, let's say they show you a phase diagram at this position, so you know this will form a sinusoidal wave of I equals to negative I naught sine omega t, isn't it? Why? Because at this position, it is here. So it is going to move down, right? At this position, so after this, it's going to go down and then it's going to go up, right? So the increasing in value, decreasing in value, because we will also always measure the vertical component of this vector. Then the value will increase and decrease and make a complete cycle. So by looking at the graph, we know this is related to I equals to negative I naught sine omega t. And we can also write this equation in the form of I naught sine omega with reference to sine omega t, because this is a negative sine graph. So if you want to refer to sine, so we find that sine, the position is here. So if we refer to this point, this vector is behind sine graph by pi radian, or in front of this point by pi radian or behind this point by pi radian. So meaning I can write either positive or negative pi. Positive will represent lead in front. Negative will represent, that's my negative, okay, will represent lags. Okay, that is about a phasor diagram. So we can use like this, meaning this is a phasor diagram kit. So this will represent the current. And this will represent the voltage. So at this position, I say that current is a sine graph. Okay, voltage will be a cos graph. So from phasor diagram, you can form an equation, a sinusoidal equation for the alternating source of voltage or alternating source of current. Okay, so we will have a few types of outcome. Meaning for this graph, you know, the phasor, the vector is at this position initially, isn't it? Then it will produce a cos graph. Okay, like for this. Okay. Oh. Okay. For this, we know the vector is at this position. So as it rotates, always rotate anti-clockwise. It will always rotate anti-clockwise. So the graph produced will be, or the wave produced will be this form. Negative cos graph. Okay. Please note that you don't really have to draw the circle for a phasor diagram. You can just represent the phasor diagram with arrow. With a line and with arrow, that will do. Let's say this is to represent current, this is to represent voltage, that will do lah. If you don't do the circle, it's okay, no problem. Okay. All right. So I'll move on to circuit. So for alternating current, we are only going to analyze using three devices or three components. They are resistor. So I will use a resistor. This will represent resistor, and then capacitor, and also an inductor. So let me start with resistor. So I will call the alternating circuit connected to a resistor. We will call this a pure resistor circuit. Okay, so we have a source voltage. I usually like to represent source voltage with Vs or just V. Okay, I'll use V. So we know, since resistor is only connected directly to the source voltage, meaning the voltage across the resistor, VR, is equal to the source voltage. Meaning if you discuss this value and this value, for this case, they are the same. Okay, so I'll just leave it as V. All right, so the current that flows in the circuit will be our alternating current, meaning at first half cycle, maybe the positive terminal is on the left, and for the second half cycle, maybe it will change, so it will become negative here and positive here, so our current will flow the other way around, and it keeps on changing periodically. Okay, so we know that if I were to take my current at time t equals to 0 seconds, maybe I have my current starting from equilibrium position. So I will have I equals to I naught sine omega t, meaning the wave produced is a sine graph. If I start here, meaning if I start measuring the current at this position, my phasor diagram at this position, so my graph should be a sine graph. If it is a sine graph, then the equation related will be I equals to I naught sine omega t. Okay, so now in order to find the voltage across the resistor or the source voltage, in this case they are the same. For this case only, they are the same. Okay, so we will use Ohm's law. So Ohm's law, it says that I equals to current multiplied with the resistance. So the current here is what? The current here is I naught sine omega t. So multiply with resistance. So what do we have? We have, okay, let me write properly. Okay, we have I equals to I naught sine omega t, meaning instantaneous current is I equals to I naught sine omega t. So what about my instantaneous voltage? Meaning voltage at any time lah. So equals to I multiply with resistance. So what is I? Of course, if this is an instantaneous value, this has to be an instantaneous value as well lah. So it will be I naught, I just substitute sine omega t multiply with resistance. So when I rearrange, I get I naught R sine omega t. So I know the value in front of a sine function will always be the maximum value of the quantity that we talk about. So our quantity here is voltage. That means this value has to be the maximum value of voltage. So V equals to V naught sine omega t. Meaning we obtain V naught is actually equals to I naught R. So in order to calculate R, resistance, we will take the maximum value of voltage divided by the maximum voltage value of current. So we will get the value of R. Okay. So R is the opposition to the flow of alternating current due to a resistor. Then we also find that for a pure resistor, if the current is I equals to I naught sine omega t, V will become V naught sine omega t. So if I were to find the phase difference, meaning the difference between the two phase, this is phase, this is also called phase, meaning the phase difference between V and I, so it will be omega t minus omega t. So we get 0, meaning the phase angle between current and voltage is 0. So we say that the voltage is in phase with current in the circuit. That means, yeah lah, if you look at the graph, current, the graph is a sinusoidal graph. Then voltage is also a sinusoidal graph. So if by looking at the graph, it's very obvious they are in phase. Okay? So this is about pure resistor, meaning circuit with only resistor in it. So the phasor diagram for a pure resistor circuit will be current and voltage. It doesn't matter. You can draw V and then I. It doesn't matter because we don't really know the value. Meaning, if let's say I have a pure resistor circuit, but my current is I equals to I naught cos omega t, then I know my phasor diagram for I is at this position. Then I know current and voltage are in phase. That means definitely the equation for V will be V naught cos omega t. So if it is a cos graph, then my voltage position will always also be here. So if I combine, that means I have I and then my V. So this is a phasor diagram for current and voltage. Now we are going to continue with pure capacitor. Pure capacitor meaning our alternating source is connected to a capacitor only. No other component, only capacitor. So same here, the source voltage will equal to the voltage across the capacitor and the current will flow through the capacitor. Okay, so I will take the initial equation. I will take voltage as my initial equation, which is V equals V naught sine omega t. Okay, so we know that the charge accumulated on the capacitor is related with the voltage across the capacitor, which is Q equals to capacitance multiplied with instantaneous voltage. So equal C multiplied with V naught sine omega t. Since current is the rate of change of charge flow in the circuit, so equals d over dt. Q meaning our Q is CV naught sine omega t. So equal meaning capacitance is a constant, V naught is a constant, so I can take it out. That means we only differentiate towards sine function of sine. So when we differentiate sine omega t, we will get C V naught omega cos omega t. Oh, you cannot see. So let me write here. So we have I equal C V naught, differentiate omega t, you get omega, differentiate sine omega t, you get cos omega t. So we can compare, as usual, we can compare this equation with a cos, meaning this will represent maximum value of current or peak value of current. So I naught here is equals to CV naught omega. Okay, let us analyze the two equations first before we go further. That means we started off with V equals to V naught sine omega t, and then our current will be I naught cos omega t. So in order to compare the phase angle or phase difference, we cannot compare using sine function and cos function. You must make sure that if this is sine, then this also has to be in terms of sine. So we know that cos can also be written in terms of sine, meaning sine omega t plus pi per 2. Why is it so? Because sine is at this position, cos is at this position. Meaning we say that cos, if you are at this position, meaning this position is faster than this point. This point is faster than this point by pi per 2. So leading, so we put a plus sign. Okay, so now we can calculate the phase difference, meaning change in phase equal omega t minus omega t plus pi per 2. So what did you get? Omega t minus omega t minus pi per 2. So it is negative pi per 2 radian. Negative here shows us that, or tells us that voltage, because we take the phase of the timing of the voltage and minus with the timing of the current. So meaning to tell us that voltage lags current by pi per 2 radian or 90 degrees. Okay? Meaning if you use a phasor diagram, current will be at cos position, voltage will be at sine position. We can say V lags I by 90 degree or pi per 2 radian or pi per 2 radian, or we can also say current leads voltage by 90 degree or pi per 2 radian. Meaning if you want to talk in terms of a current, then you will take the phase of current and minus with the phase of voltage. Meaning like this. Phase difference equal, the phase of current is omega t plus pi per 2 minus omega t. So you will get positive pi per 2 radian. So the positive here meaning leading. So meaning I leads V, because you are talking about current first, then only you talk about voltage. So we get the relationship for pure capacitor. Now we proceed to discuss about the resistance to the flow of current. Since just now we get I naught is equal to, just now we get our equation I equal CV naught omega cos omega t. So we compare with I naught cos omega t. So we find that I naught equals CV naught omega, or V naught equals I naught multiply with 1 over omega c. Right? If you look at this, it's almost similar like V equals to IR, right? Voltage equals current multiplied with the resistance of the circuit, if you are using a resistor. But since here we are using a capacitor, so it's not not suitable to use the resistance. So the resistance or the opposition of alternating current due to a capacitor, we call it reactance. Reactance. So sudah tersusun. Okay. So meaning this is called reactance of capacitor, or we call it capacitive reactance also can. So this, the unit of reactance will be the same as the unit of resistance, because both are the opposition to the flow of alternating current. So the unit will be in ohm. So from here, when we compare, you find that reactance of capacitor or capacitive reactance will equal to 1 over angular frequency multiplied with capacitance, or also equal to 1 over 2 pi fc. Why? Because angular frequency can be written in terms of frequency. So from here, we find that, reactance of capacitor or capacitive reactance is inversely proportional to frequency. Meaning if I sketch a reactance against frequency graph, then the graph will look like this. So that is about pure capacitor circuit. Now we will move on to a pure inductor. Pure inductor meaning simply connecting an alternating source to a solenoid. Solenoid will represent an inductor. So this circuit only has the solenoid in it. So same here, the voltage, the source voltage will equal to the value of the voltage across the inductor, and current, alternating current flows through it. So let me start by taking current as I equals to I naught sine omega t. So as we know, if there are current changing in the inductor, then the phenomenon of self-induction will occur. If self-induction occur, meaning there will be an induced EMF. So we will start by using induced EMF equals negative inductance di over dt. So induced EMF equals in negative inductance d, meaning differentiate current. Current is what? Current is, just now we take as I equals to I naught sine omega t, isn't it? So is I naught sine omega t. So I naught is a constant, so I'm going to take it out. So I naught. So meaning here, I just have to differentiate towards sine omega t. So what did you get after you differentiate? So we have negative L I naught omega. So when you differentiate sine omega t, you will get cos omega t. Okay. So we know that the voltage across the inductor is always opposing the change that produces, the induced EMF is always opposing the change that produces it at. So the voltage that produces it is voltage across the inductor. So equals negative induced EMF. So equal negative L I naught inductance multiply with peak current multiply with angular frequency cos omega t. So we get L I naught omega cos omega t. So as we say here, the quantity in front of a cos function is always the maximum value for this quantity. So meaning this will be V naught peak voltage cos omega t. So what did you get? Meaning we conclude that V naught here is equals to, cannot see. So V naught here is equals to L I naught omega. Okay, let us analyze the equation before we go further. So we find that just now we started off with I equals to I naught sine omega t. Then we find that the voltage across inductor is V equals to V naught cos omega t. That means in order to analyze about phase difference, you cannot have sine and cos. So you must make sure either this is cos and cos or this is sine and sine. So let me use V naught equals to sine omega t plus pi per 2. Okay, so the phase difference equal to, let me take the phase of voltage and minus with the phase of current. That means omega t plus pi per 2 minus omega t. So I get positive pi per 2 radian. Meaning to tell you positive here, just now I take the phase of voltage, meaning voltage leads current by pi per 2 radian or 90 degree. Okay, now we proceed. We proceed to our equation just now where we have V naught equals to L I naught omega. As usual, we will compare to, we will rearrange. That means I have I naught maybe I arrange like that, omega L. Then I compare using Ohm's law relation. So V equals to I naught XL. So for the opposition of the flow of alternating current due to an inductor, I will call it, we call it, not me, we call it reactance of inductor, or you can also call it inductive reactance. So remember, it opposes the flow of alternating current. That's why the unit should be in ohm, same as resistor. Okay, same as resistance. All right. So what did you get? Meaning, reactance of inductor is equal to omega L, or equal to 2 pi Fl, because omega is 2 times pi times with frequency. So if I were to sketch a graph of reactance against frequency, then I will get a directly proportional graph, because XL is directly proportional to inductance, because this is a constant, and the frequency is also a constant. Therefore, reactance of inductor will be directly proportional to the inductance of the circuit. Okay, are you still with me? Jom, cayo, we can do it. So let's say now I have 3 devices in a circuit. Oh, I lompat we can have combination of RL circuit, we can have combination of RC circuit, but we are not, meaning the combination for LC circuit is not in your syllabus, okay? So we just have RL circuit or RC circuit. So I'm going to jump, do a quantum leap. So I'm going to do RCL circuit, one shot. Okay, are you with me? Are you ready? So we will have the alternating current source. Okay, then connected to a resistor. Okay, and then connected to a capacitor, and connected to an inductor. Looks scary, right? Don't worry lah, not so scary. Okay, so please note that here we have 4 types of voltage. 4 types of voltage, my dears. Okay, meaning we have source voltage. I'll put a V. We have voltage across resistor. We also have voltage across capacitor and voltage across inductor. 4 types of voltage, and then 1 type of current. Current only 1. Then you must remember, each voltage will carry 3 types of value, meaning each voltage, it will have instantaneous value. If you talk about instantaneous value, maksudnya it simply means voltage in terms of sine, function of sine graph lah, meaning V equals to V naught sine omega t, meaning your equation in terms of time. That will be your instantaneous. Ejaan salah. Instantaneous. Alright. Okay. So the second value will be the root mean square value, means the effective value. And the third value will be the maximum value. So same goes for here. This one also the same. You have 3. You have the instantaneous value. You have the root mean square value, and also the peak value. Also the same goes for voltage across resistor, voltage across capacitor, and voltage across inductor. Okay, so I'm going to erase this. That means, what do we have? we have voltage across resistor, which is current that flows in the circuit multiply with resistance. Then we have voltage across capacitor equal current multiply with reactance of capacitor. Then we have voltage across inductor, so equal current multiply with reactance of inductor. As simple as that lah, not that difficult, isn't it? Can? Don't panic simple only. So now back to our concept. Do you still remember? For pure resistor, the timing of current and voltage across a resistor is the same. Meaning, if the current is at sign, that means the voltage across resistor is also at sign. But if the current is at sign for capacitor, the voltage will be at negative cos. Masihkah kau ingat? Voltage across capacitor lags current by 90 degree. As for inductor, if the current is at sign, then, if the current is at sign, then the voltage will be at positive cos. Are you okay? Meaning if you want to write in terms of sinusoidal equation, then it becomes like that lah. If you start with I equals to I naught sine omega t, then your V across R will be V naught R, sine omega t. Voltage across capacitor will be negative V naught C cos omega t. Or I can write V naught C sine omega t minus pi per 2. Also can? Also can. Then for voltage across inductor, no space, so I'm going to take here. So voltage across inductor will be V naught L cos omega t or V naught L sine omega t plus pi per 2. Also can. Okay, settle lah. So I don't want to make it so complicated. So I'm just going to use the phasor diagram. Meaning for an RCL circuit, if I use current as a reference, my voltage across resistor will sit here. Voltage across inductor, if the voltage is bigger than voltage across capacitor, then I draw this longer. So VL, and this one slightly shorter. Since this is a vector and they are in the same line, meaning I can just get the resultant of VL and VC, meaning this vector minus this vector. Let me have a shorter one so that you can see. Okay, here, let me make it a bit shorter so you can see clearly. So meaning this length minus this line. So we will get a new vector here. So what do you call this vector? You call this vector VL minus VC. So actually, you can just erase this and then you just write VL minus VC. Then this is your VR. So the resultant of these two vectors, because it's a vector, so the resultant of these two vectors we will use a parallelogram. So meaning this vector add up with this vector. This vector add up with this vector. So the resultant will be here. So what is this? This is the source voltage. So the source voltage, if it's 6 here with an angle, phase angle Bukan angel Phase angle is the angle between current and source voltage. Phase angle is the angle between current and source voltage. Boleh? Boleh kah? Okay, settle lah. That means if you want to write in terms of sign equation, it means instantaneous source voltage, then it will become V equals to V naught sine omega t plus phi. Meaning source voltage leads current by a phase angle phi. Itu maksudnya lah. Okay. So, now, if I want to calculate this value, I will find angka Pythagoras lah. Mestilah. So, this is a source voltage. So, this is my voltage across resistor. This is voltage across inductor minus voltage across capacitor. Of course, if this value is bigger, then it will be voltage across capacitor minus voltage across inductor lah. So you depends on the value given. Okay, so I can find my source voltage, which is square root VR squared plus VL minus VC square. Simple as that. So here I can use Ohm's law. I can substitute with I R square plus I XL, remember, minus I XC square. See, where's my square? Is here. Buka mata besar-besar tengok. Okay, now I can expand. After I expand, what do I get? So V equal I square R square plus, this one I can factorize, right? I can do this, I square XL minus XC square. Don't understand? Ask your friend who are good in maths. Okay, so I can take out I, betul? Never mind, you can refer to my notes. I have the details there. So R square plus XL minus XC square. Boleh kan? So meaning the voltage, source voltage, you can use this equation. You can also use the basic equation. If they give you VR, you can use this VL minus VC square. If they give you the value in terms of voltage, you can use this equation. If they give you the value in terms of resistance, reactance, then you can use this equation. Okay? So, we find that once again, I can compare this with Ohm's law, meaning V equals to I, and the opposition to the flow of current due to resistance, due to resistor, due to capacitor, due to inductor. Due to these three components, we call it impedance. Impedance is the opposition to the flow of alternating current due to either resistor, capacitor, or inductor. So we call it impedance. So what is impedance? So you can see from here. So impedance is square root R square plus XL minus XC square. Okay? Okay, using the same phasor diagram, meaning VL minus VC, and then VR. Okay, compared to current as a reference. Current is always our reference, okay? So, a parallelogram. This is your V, this is the angle. Meaning, we can also find the phase angle. So, phase angle is, it means I can use tangent. You want to use tangent, can. You want to use sine, can. You want to use cosine, also can, no problem. So tangent is opposite over adjacent. So your opposite is what? VL minus VC divided by VR. Meaning if you know the value of voltage across inductor, voltage across capacitor, voltage across resistor, meaning you can find the angle between source voltage and current, which is called phase angle. Phase angle lah. Okay. I can also elaborate this. That means tangent phi phase angle equals to, using Ohm's law, so IXL minus IXC divided by IR. So I factorize, so I equals to XL minus XC, okay, divided by IR. I cancel out the current, so I will get XL minus XC over R. So I also can use this equation to find, but this equation you need not memorize because it is all based on your phasor diagram. Meaning, if you have an RC circuit, that means you don't have inductor in the circuit. So your equation will become negative XC over R. Why negative? Because negative is clockwise, below clockwise from current. Maksudnya it is below current or lags current. Means this angle will sit here. See? This is for RC circuit. So it depends on your circuit lah. That means you just play with the equation. If you have RL circuit, that means this value does not exist. Things like that lah. Okay? So now we are going to see about impedance. We're going to take a look at impedance. So impedance, the symbol is capital Z. So the meaning of impedance is the opposition to the flow of alternating current due to a resistor, an inductor, or a capacitor, right? But the definition of impedance is impedance is defined as ratio of root mean square voltage to root mean square current. This is the definition. Okay, of course, this one comes from Ohm's law lah. V equals to IZ. Okay, so from here we can gain another equation by substituting V root mean square, which is V naught over cert 2. Masihkah kau ingat? And then I naught over cert 2. Still remember? Okay, so equal V naught over cert 2 divide by I naught over cert 2. So you have V naught over cert 2 times cert 2. Correct. Cert 2 divided by I naught. Tiba-tiba terjam, terbutter, termargarine. Okay, let me write again. Meaning Z equal VRMS over IRMS. So equal V naught over cert 2 divided by I naught over cert 2. So equal V naught over cert 2 divided by I naught over cert 2. So you get V naught over cert 2 times cert 2 divided by I naught. Oh, that means you find that your cert 2 you can cancel out. Once you cancel out, what do you get? That means V root mean square equals to over I root mean square is also equal to V naught over I naught. But if they ask you for definition is only this. But from the definition, we find that impedance is also equal to peak voltage divided by peak current. Okay? Meaning, if like that, meaning very simple lah. Meaning, if you are using root mean square voltage, that means Your partner has to be root mean square current. Itu je. If you are using peak current, then your current, peak voltage, then your current has to be also peak value. You cannot have here RMS, then here peak value. Then it's not correct lah. Okay, so that is about impedance. Okay, let's refer back to our impedance equation where Z equals to square root of resistance square plus bracket inductive reactance minus capacitive reactance bracket square. So I'm going to write this in terms of frequency, meaning inductive reactance can be written as 2 pi FL and capacitive reactance can be substituted with 1 over 2 pi FC. So if the value of frequency decreases to 0, we find that the value of Z will increase to infinity. Why? Because if this value is 0, that means this quantity will be 0. But if this value is 0, the frequency here is 0, you find that 1 over 0 will give you a very large value. And it is infinity but square, so this will be positive infinity, which is very much bigger than the value of R. So Z will become infinity. If frequency is increased to infinity, we find that Z impedance will also become infinity. Oh, why? Because when frequency is infinity, you find that inductive reactance will become infinity, but 1 over infinity will become 0. So square of this value will be very large compared to resistance. So this is almost negligible. So therefore the value of impedance will become infinity. So from here, we can sketch a graph for impedance against frequency graph. Impedance against frequency graph, you find that the value of Z increases to infinity, and when the value of frequency decreases to 0, and the value of impedance increases to infinity as well when the value of frequency increases to infinity. But the graph for resistance is a constant because resistance does not depend on the value of frequency. So you find that at a certain point, the value of impedance will equal the value of R. So by looking at this equation, impedance will only be equal to the value of R when this quantity is 0. So if XL minus XC is 0, if XL minus XC is 0, meaning the value of XL has to be equal the value of XC. So this will happen at a certain frequency, meaning 2 pi f L equal 2 pi f, 1 over 2 pi fc, meaning this value will be equal at a certain frequency. So this phenomena, we call it resonance. So this is Xc, which is inversely proportional to frequency. Okay, and for inductor or reactance of inductor or inductive reactance, it is directly proportional to frequency. So the graph is a straight line. Forget to use different color. Okay, it's a straight line. So this point, the value is Xc. This one is XL proportional to frequency. So this is impedance. So this is what we call resonant resonant frequency. So this frequency occurs when the value of capacitive reactance equal the value of inductive reactance. So if the value of capacitive reactance equal the value of inductive reactance, meaning the value of impedance at this point will equal the value of Z shown in the graph. Okay, so this phenomena we call resonance. So at resonance, what do you have? The value of impedance, which is R square plus XL minus XC square. So we know at resonance, the value of XL equal to XC. That means Z will equal to R. Correct, right? Isn't it? Then the value of current VI equals to V over Z. So the value of current, because this will be the minimum value. This will be the minimum value. Because this is 0, so this will be the smallest value. So if this is the smallest value, that means your current will be the maximum value, meaning current will be maximum at resonance. And then if Z impedance is equals to R, then we find that source voltage, usually source voltage is not in phase with current for RC circuit or for L circuit or for RCL circuit. But if resonance occur for RCL circuit, then we find that source voltage is in phase with current. So these are the information you need to know. At resonance occurs when inductive reactance equal capacitive reactance, and then the current is maximum. The impedance is the minimum value, is at minimum value, and then source voltage is in phase with current. These are the information that you need to know. Okay, so how to calculate resonant frequency? So we can have XC or XL equals to XC, reactance of inductor equal reactance of capacitor. So this is 1 over omega C. This is omega L. So I can have omega square equals 1 over LC, or omega angular frequency equals to 1 over square root of LC. Oh, so you get omega equal 1 over square LC. So what is angular frequency? Angular frequency can be written in terms of resonant frequency. So it's 2 pi FR. So this is resonant frequency equal 1 over square root of LC. So resonant frequency is 1 over 2 pi square LC. Ta-da! As simple as that. So if the question asks you to calculate resonant frequency, you can just use this equation. So you find that if XC equals to XL, you find that VC is also equal to VL. Do you believe me? See? Why? Because current in the circuit is the same. So I can multiply current both sides. I can multiply current on each side. So I get IXL. So current multiplied with capacitive reactance is equals to voltage across capacitor, and then current multiplied with inductive reactance is also equal to voltage across inductor. Okay, the last part of this chapter, which is power. So we find that current, there are three types of value. There are instantaneous current, meaning current in terms of time. That means you have like I equals to I naught sine omega t. That's called instantaneous current, meaning current in terms of time, meaning current as a function of time. Means the time will influence the value of current. Okay. Then we have root mean square value of current. Then we have maximum current. So you find that, oh, the maximum, the effective current that we use in the circuit is root mean square current. So we think that, okay, in that case, maybe power we also have instantaneous power. Okay, that means power as a function of time. We also have root mean square power. Root mean square power meaning IRMS multiply with IV RMS. Just like that. Okay. Then maybe we have, okay, maximum power. So will be I naught V naught. Okay. So we thought, oh, that means the effective power or power that we receive will be root mean square power. But when we do the experiment and then we get the result, we find that, no, it's not true. Not true for all cases. True only for certain cases. So like this, what is the effective power? So rupa-rupanya, the effective value for power is actually called average power. Meaning when we carry out the experiment, we find that we give the circuit, let's say we give the circuit 2 watt, but we only get less than 2 watt. What we get is less than 2 watt. We didn't get actually 2 watt. So why? Meaning the value that we get is PRMS, but reduced by a factor of cos phi. So this we call the power factor. Meaning the actual value that we receive from the circuit is actually the root mean square power multiplied with a factor of cos phi. That is the actual value that we get. So let us analyze. Meaning this will be IRMS multiplied with VRMS. So remember that cos phi can be written in terms of R over Z using the phasor diagram. Meaning, if I have the RCL circuit, that means you have your VL minus VC here, and then your VR is here. So your source voltage is here, meaning I also can do a phasor diagram using reactance. That means my resistance is here, my XC, XL minus XC, and then my impedance is here. Because current is the same, because this is a series circuit, so the current in the circuit is the same. So you find that, cos phi is what? Cos phi is adjacent divided by hypotenuse. So it's R over Z. Adjacent divided by hypotenuse. So it's R over Z. Okay. Now, this can be written as, this is source voltage. Didn't say anything, meaning it's a source voltage. Otherwise, you will have 4 types of voltage. Source voltage, V, VR, VC, VL. 4 types of voltage. It didn't mention anything, meaning the voltage is a source voltage. If the question didn't say anything, meaning the voltage given is the effective value or the stable value of voltage, meaning it is the root mean square voltage as well. Okay? Did you get it? Right? So I can write this as IRMS multiply with IRMS Z. So multiply with R over Z. So what happened to your impedance? Impedance will be cancel out. Cancel out, cancel out. So we have another equation for average power. Average power equal I RMS square R. So this is the most user-friendly equation to calculate power dissipated, power absorbed, power supply, all same meaning. This is the most user-friendly. Okay? Otherwise, you will have to use this equation also can. If you use this equation, then you need to know the value of phase angle. For RCL circuit, you have to calculate the value of phase angle. But for RC circuit, you also have to calculate. But for pure resistor, you find that the angle is 0 because pure resistor, phase angle is 0. So cos 0 is how much? 1. That means for pure resistor, dissipated power is actually the power supplied to the circuit. It's not reduced by a factor of cos 1 because cos 0 is 1. But for a pure capacitor and pure inductor, you find that the phase angle is 90 degree. So cos 90 degree is how much? Cos 90 degree is 0. So you find that inductor and capacitor does not dissipate power. They absorb, then they return back to the circuit. So the average power is 0. Okay? These are the concept lah. Alright. So I can write average power atau cos phi is also equal P real divided by P apparent. So we just use the symbol lah, PR over P apparent. PR over PA. Apparent means the one that we thought that is the value lah. Apparent means this one it means P average. This one means apparent here means P RMS. So if P average, what is the equation? That means cos phi equal P average divided by P RMS, meaning what? Meaning P RMS cos phi divided by P RMS. So correct lah, dapat balik. Okay, so settle. Okay, we settle everything for chapter 6. That means what you really need to know is for a pure resistor, the voltage across resistor is in phase with current. Very important. In phase meaning the angle is 0 degree. Bukan the angle, the angle is 0 degree. Then for pure capacitor, the phase angle is 90 degree, or the voltage across capacitor lags current by 90 degree. For pure inductor, voltage across inductor leads current by 90 degree. These are the concepts that you need to know. So from there, then you will form a phasor diagram for RCL circuit or RL circuit. For example, okay, let me take RL circuit. Okay, RL circuit. So you see here we have resistance, then you have inductor. So we have 3 types of voltage here. We have V source, we have voltage across resistor, we have voltage across inductor. So this is not like direct current. Direct current, we say, oh, V equals to VR plus VL. So in this case, it's not true. Why is it not true? Because the timing is not the same. This one, the timing is the same with the source voltage, but this, the timing is not the same. This one, the voltage is faster than the current by 90 degrees. That's why if you do the phasor diagram, so the concept is, if you take current as a reference, then your voltage across resistor will sit here. Then the voltage across inductor will sit here. So you do a parallelogram. Parallelogram has to be between the voltage, not with the current. Okay, so that means the source voltage will be here. So the phase angle will be here. Meaning for RL circuit, you find that source voltage leads current by phase angle. Phase angle is the angle between voltage and current. So you can just find you can use Pythagoras theorem to find the value of source voltage. You can also use trigonometry to find the value of phase angle. Then you can also calculate your average power if you want using PRMS cos phi where you need the angle, or you can just use I square RMS R to calculate the average power or the real power. Means power dissipated by the resistor. Meaning you find that in this circuit, the power that is actually the power that we receive actually only come from the resistor. It doesn't come from the inductor. It doesn't come from the capacitor. Okay, so that's all. I hope you stay cheerful and healthy. Okay, take care of yourself. Right, so few more weeks to go. Just struggle and then get over with it. Okay, so please take care. So I'll stop here. Thank you very much for your time.